Okay. We'll go ahead and get started. So thank you guys for joining us today. I'm Dr. Darcy Snowden. I'm the director of NESP, the Northwest Earth and Space Sciences Pathways program. And you guys are joining us today as part of the Artemis Roads 3 Challenge, which is a student challenge thinking about sending humans back to the moon, focused on NASA's Artemis mission. And today we've got our first official NASA expert talk here. We're joined by Ross Kovtun, who's joining us from Texas. So he's a lunar geotechnical scientist at NASA's Johnson Space Center, which is in Houston, Texas. And Ross will tell you a little bit about how he got to NASA, but his path is anything but conventional, like a lot of yours might be. He first earned his degree in history from California State University, Northridge, and then he actually got his master's in business, an MBA. But then he took a turn towards geology and he did some graduate work studying both mass extinctions on the Earth in California and also the Gale crater on Mars. Some of you guys might know about the Gale crater at Rice University, which is in Texas. And today, now at Johnson Space Center, he's playing a key role in preparing NASA for its mission back to Mars. And I'm really excited to learn more about his journey and what he's working on now. So everybody, please join me in welcoming Ross. And I'll switch it over to you, Ross. Thanks for joining us.
Yeah, thanks for the introduction. I will say one catch on that. I think he said back to Mars, which is the end goal potentially, but right now we are working primarily on the moon,
Right.
getting back to the moon, and I'm going to be talking a lot today about the moon and basically just lunar exploration, sort of past lunar exploration and future lunar exploration, where we're sort of going with the Artemis missions. So let me go ahead and share my screen. One second. So, so yeah, today I'm going to be talking to you all about the exploration of the moon and taking a quick look back and what we learned from going to the moon with the Apollo missions and everything we learned from a science perspective, but also from just a space exploration perspective. And then I'm also going to be talking a little bit about where we're going with the future Artemis missions. And we're already, in the middle, or not in the middle, but towards the beginning of our Artemis campaign of getting boots back on the moon and onto Mars at some point. So before I kind of dig into that, a really quick sort of background, and I'll leave all the details for the Q&A if folks have questions. But basically, you kind of heard in the introduction that I have a sort of unusual pathway to being where I am today. And I will say, even where I am today is a little bit of an unusual area because my day-to-day job title is a lunar geotechnical scientist. And what that really means is I study both planetary science from a geology perspective, but I also incorporate engineering in my day-to-day job. So I look at things on the lunar surface that, once we get to the lunar surface with hardware, with astronauts, they'll interact with the surface. And my job is to basically, through testing or through development of what we call planetary analogs, to help them perform any kind of science on the lunar surface or any kind of exploration on the lunar surface. So this is my general background. I got my degrees in history, my undergrad, and graduate degrees in geology, and with a focus both on earth sciences, but also planetary sciences. And then I worked for a number of years in industry, actually doing engineering geology work. So whenever you see big buildings being built all over the place, before those buildings are built, usually engineering geologists will go and actually inspect the subsurface or the underground areas, the soil, the rocks, everything that the building will eventually be sitting on top of. So now I'm going to dive right into the Apollo missions. So if you're not familiar with the Apollo missions, these were 6 missions that occurred between 1961 and 1972 that sent US astronauts to the lunar surface in various regions of the lunar surface to perform science missions, but also exploration missions, and also just to get boots on the ground and really be able to explore a world that no one had ever seen before in person up to that point. And this is just a really nice picture of what, the lunar exploration really envelops. You can see there's a rover there that the astronaut can drive on. The astronaut himself is doing a lot of work, and there's also a way to get to the lunar surface through a landing module. So these are the Apollo landing sites that we actually visited in on the regions on the moon. And the first thing that you notice, obviously, there's 6 stars there. So each mission from 11 to 17, obviously not 13 is not on there. Great movie to watch if you're interested in Apollo 13. See why we don't have an Apollo 13 star on this lunarscape. But these are the 6 missions that sent U.S. astronauts to the moon, to the surface, to do exploration, science exploration. And what you'll notice is they're all kind of congested in one region of the moon, sort of the central region of the moon, that if you look up in the night sky when there's a full moon, you'll be able to see this almost square on from where you're at in North America. And most of the places that you see are kind of where they went are in these low-lying, sort of darker regions, which we call the mare. So only really the Apollo 16, where you see that star, it kind of looks like it's on a different layer. It looks a little bit more pockmarked with craters, and it looks a little bit lighter in color. And we actually call that the lunar highlands. So they're a bit older area, a bit higher topography, a little bit more of these crater features, a little bit rougher in general. And we'll go into that a little bit here. So this is what one single mission would look like. If you're looking overhead, this is just Apollo 15. And on the left-hand map side, you kind of see an orbiter image of the Apollo 15 landing site. And you can see the lander sort of right in the middle of that image. And you can see on the ground, there's all these tire tracks. That's actually the lunar roving vehicle that was on the surface, starting with Apollo 15, that was able to basically be driven by the astronauts and give them access to all these regions that were a bit further away from where they landed. They also had a experiment package called the Apollo Lunar Surface Experiment Package, or LSAP. They got a lot of really good data, what we call in situ, or sort of in place data on the lunar surface. And so we received a lot of data back from those sort of in place measurements, but also from return samples with Apollo. And we learned a lot of things that we didn't know before going to the lunar surface. And just really quickly, the things that we learned were that, the moon likely formed when we had a large, about a Mars-sized object basically hit the Earth about 4.5 billion years ago and took off a chunk of material from the early Earth and basically formed a ring around the Earth that eventually kind of glued itself together to form the moon that we see today. And the moon's surface is probably very old. Just the surface is probably on the order of billions of years old. And all the top of the surface is blanketed by this loose, sort of fluffy material that we call the lunar regolith. And I mentioned before that the moon sort of has these 2 general regions, this darker area, this lighter area. Now, the darker area is what we call the lunar mare. And they're basically made up of what you can see if you ever go visit Hawaii where I saw some folks here were from Idaho, lots of old volcanic activity out there as well. And you have these volcanic basalts, or these basalt flows, where you have a bunch of lava just kind of slowly spewing out of the ground and covering a large surface area. And that's what these volcanic mare on the lunar surface are like. And most of it is billions of years old. And then the brighter areas of the moon, like I said before, are called the lunar highlands. And they're actually even older than the mare. And we think that that is sort of kind of like what the moon was mainly composed of prior to the volcanoes sort of going up, erupting, and going on top of the material that was on the lunar, that composed the moon initially. So this is our sort of best guess at how the moon formed. So like I explained before, this is called the giant impact hypothesis, or if you want, the big whack, right? So the idea is that you have a early Earth 4.5 billion years ago, and then you have a smaller size object like Mars that basically impacts the early Earth, takes off a bunch of molten lava material, just and rocky material, and it basically, because of gravity, it sort of, this material sort of spews out from the Earth, and it gets trapped in an orbit around the Earth. And over a long period of time, this material sort of comes back together, gets glued back together, coalesces, and turns into what we now call our moon. And the moon is, was kind of similar to the Earth at some point. It had basically a really deep of liquid, what we call a magma ocean. So if you can imagine just hot lava, it's basically covering the entire surface of the moon at some point. But because that hot lava is exposed to basically just the vacuum of space, eventually that top layer sort of cools, and creates a sort of crust. So a lot of that magma ocean turns into crust, and then you start having a gradual cooling of that hot magma ocean. That magma ocean turns into minerals and rocks, and they get separated out, and you basically have what we can see at the what we can see of the subsurface on the moon now, which is basically a fully rocky body with really no magma ocean present currently. And we also see a period of when we had really, really large collisions between objects that were flying around between the moon and Earth and in space, that were impacting the moon and creating what we call these large impact basins. And these are really huge, thousands of kilometers in diameter, really, really big things, really deep, that basically are these markers that we use whenever we look at the lunar surface. If you have a telescope, you can kind of find these. You can map these really quickly. You can find places on the lunar surface that are still, visible after billions of years of bombardment, that show as these really massive basins. But when you actually go on the surface, and what we see even from orbit is really only the top layer of the moon, which is composed of this really fine grain, kind of almost sandy, even finer than sand material that we call the lunar regolith. This stuff can be up to 10 meters deep, and maybe even deeper in some areas, shallower in other areas. But that's really the only thing we've ever really walked on with all the Apollo missions. The only things that we've returned back from the Apollo missions are basically part of this topmost layer of regolith that that we've explored so far. We haven't really been able to get deep down enough to get samples of things below that 10-meter regolith bed. And this is kind of what lunar rocks look like. Interestingly enough, you can find rocks like this in composition on Earth. There are places that have these, like I said before, like these basaltic rocks that are basically just these lava rocks that crystallize or basically cool down when they're exposed to the surface. That's kind of what they look like. We also have these anorthosites that make up the uh, large part of the lunar highlands, which we can find these sort of rocks in Greenland, in Canada, in Montana. So they're here, terrestrial rocks here, but they are slightly different in composition. There are certain things from a chemical perspective, from a mineralogical perspective, that are slightly different. And the biggest oddity there is when we look at these individual grains, are these grains called agglutinates. These are really weird kind of grains that we don't really have on the Earth's surface because we have an atmosphere. So any little micro meteorite, like a tiny little rock that's just kind of flying through space, gets burnt up in our atmosphere. It doesn't usually really make it to the surface. On the moon, there's no atmosphere, there's no air, it's all just vacuum. So these little uh, tiny little microscopic meteoroids will actually impact the ground, and basically whatever they hit, they kind of melt that grain, and they kind of turn into like a little globby, glassy, rocky little grain that's really, really cool looking, very weird looking, but is also very unique to the lunar surface. Not something that we can really have here on Earth. The other thing to put into perspective is, I mean, the Earth is big. It's about the size of North and South America put together, which is a lot of land, but it is much smaller than Earth. So we have to keep that in mind whenever we talk about doing exploration and where we go. And so previously, I've shown you this before, these Apollo landing sites, and they're all sort of clustered together and they cover this little tight grouping on the lunar surface. They're all at about the equatorial region, or around the middle point of the moon. And if you put those same Apollo landing sites on a map of the United States, in the chat, I heard people from Texas, people from New Mexico. That's sort of where we would land with all those Apollo missions if we were to land, on Earth, right, and do lunar exploration on Earth. And guess what? We would be missing the Rocky Mountains. We'd be missing the ocean. We'd be missing so many things. So the idea is, yeah, we've been there, but do we really know everything we want to know about it? And as good scientists, we always want to know more. There are tons of places that we want to go. Each one of these stars represents a place that scientists are interested in going and looking at because there's something interesting there, some kind of feature either on the surface or in the subsurface that we're able to pick up with our orbital data or remote sensing. But there are so many places that we want to go to still, and we're planning to go to some of these either through with the Artemis campaign or commercial missions going into the future. And so one of these cool features on the lunar surface that I'm really interested in and really excited about are caves. There are caves on the moon. We've seen at least 8 of these, what we call mare pits, which are basically the same thing. If any of you have been lucky enough to see a lava tube, they're basically just a giant lava tube, basically a hole in the ground. And you can actually get down into that hole, and there's places where you can crawl in, and it's a cave. It's covered by the surface, and it kind of is almost like like a safe spot. And these are we've seen these at different locations on the moon, mostly in that lunar mare region where it's all those basalt flows. And these are really cool. There are a lot of ideas out there for how we can use these features on the lunar surface to actually do lunar exploration and habitation. And this is just a reference. If you've never seen a lava tube in person, I highly recommend seeking one out. But this is what they look like in person. This is a lava tube in Grants, New Mexico. And these can be huge. I mean, you can fit thousands of people into some of these by the way the size of them. And they're all over the Earth. Whenever a lot of places where there are these really heavy basalt flows that are really deep, you can find lava tubes. So we did a lot of sample collection too on the lunar surface. Through all those 6 missions, we brought back about 840 pounds of rock and soil. And that sounds like a lot, and it is. And we've been using them for the last 50, 60 years to do a whole lot of really cool science. And the Johnson Space Center where I work is actually the place where all of these samples are kept, and we can give those samples out to scientists from all over the world to study these rocks and soils. The problem is, yeah, it's a lot of material, but it's nowhere near enough material if we really want to start testing hardware and suits and tools and everything that we need to do before we return back to the moon. We need to know how these things work, and we don't have enough materials to enough of the lunar samples to really do that. So one of the things that I'm involved with and that I help is to do testing of hardware, things that are going to be flying to the moon or things that are going to be used on the lunar surface, and testing them in what we call a lunar simulant, or just a material, terrestrial material, something that was mined on the Earth that we make to look and feel like the lunar surface regolith. So you can kind of see on the left-hand side a very famous boot print of the moon by Buzz Aldrin. And you can kind of see what the lunar regolith looks like with the foot imprint. And on the right is a bin of lunar simulant that's in my lab here at the Johnson Space Center in Houston. And we try to do as you know, it's 240,000-mile trip for this material. So it's understandable that we don't have that much of it left, and it's not just given out willy-nilly to whoever wants it. I would take, hundreds of kilograms of it if I could, but we have to work with what we have. And right now we have really good materials that we can do a lot of this testing in. And the way we create these simulants, these analogs for the lunar surface, is by looking at all the data that we got back from the lunar surface in the return samples, what the particle size distribution is, how big the particles are, what shape they are, what's the composition, what is the rock or the soil made out of, what kind of minerals, what's the chemistry of it. And then we take all that data, we put it together, and we create the lunar simulants to replicate or be very close to that lunar sample. And then we do a lot of testing. We test all sorts of different things, and all of these things are done in the lab that I help run at Johnson Space Center. And we test the astronaut suit materials like the gloves. We test different geology tools. So when the astronauts go to the lunar surface to explore and try to bring samples back, they're going to use a variety of tools. We test different types of metals, and we characterize the simulants. So we actually see what they're made out of and how similar they are to the lunar samples that were brought back. And the whole idea here is that eventually, from going from those Apollo missions now into the Artemis era, we're going to be going back to the moon. We're going to be exploring the moon. We're going to be using all the hardware that we're now testing on the lunar surface in the lunar environment. And we're going to be doing that in multiple missions and for a long time to come. And this is just sort of a cartoon of what something like that could look like, with astronauts, with the something that you could drive on the lunar surface, somewhere you can live on the lunar surface, somewhere you can explore, live, and drive on the lunar surface. And we're doing that with the help of a lot of different countries. And this is actually probably outdated at this point. There's probably a good number of flags that I can add to this list, but these are what we are called the Artemis Accords, which is basically just a lot of countries that have come together and agreed to go and explore the moon together in a sustainable way. And so we like I said kind of early on in the talk, we're in the middle of Artemis, the Artemis missions. We've already done the first Artemis mission, where we've sent a giant rocket to go around, orbit around the moon and come back to Earth. We've done that already. It was a big success for us. It showed that we can actually get this really long go on this really long path to the moon, get into a very, very specific orbit around the moon, and then come back to Earth as well. And Artemis 2 is the next step in this. So if we're fortunate, sometime at the end of this year, we'll be able to see the launch of Artemis 2. And the big difference here is now we're actually putting astronauts, we're putting humans into the capsule that's going to be orbiting the moon and then coming back to Earth. So now this is kind of the same thing as Artemis 1, but with people actually involved. And they'll be able to do some science as they fly by the moon, whether it's taking pictures or documenting things from their perspective on the lunar surface when they orbit it and return back to Earth. And then Artemis 3, this is kind of the big one that I'm really excited about, because this is when we get our boots on the ground. This is our Apollo 11 equivalent, where you can actually land on the lunar surface, put astronauts on the lunar surface, and do some science on the lunar surface. And this will be the first time that we're putting humans back on the moon, is with Artemis 3. And there's so many cool places that we wanted to go. But what we're going to be aiming for is really going to the lunar South Pole. So all the way at the pole, the southern pole of the moon. And it's really cool there. I mean, the light conditions, the way that the sun lights up the South Pole is unlike anything we've seen at the equators. The sun is coming at a really low angle to the South Pole, so everything is kind of in this really cool looking light and dark, like the way you see it here. There are these kind of islands of dark or islands of light and a lot of darkness, and they basically create these pockets of areas, especially in the bottom of big craters, that never see the light. They've never seen light for billions of years. And we're really hoping that in these areas, we can actually find things like frozen water, frozen ice, that we can actually dig down into and use as a resource whenever we want to live or be on the lunar surface for a long period of time. So we can do a lot of things with that material, whether you're using it as fuel for rockets instead of having to bring a lot of our own fuel back from Earth with us. We can also use it to live on the surface for growing plants, for doing lots of other things. So that's why we're going to the lunar South Pole. And this is just to show you the general kind of reason, or the missions in order of what we're going to be doing at the lunar South Pole. And we're really looking into doing things in the future, having mobility, having rovers on the lunar surface to help astronauts be able to drive around and to get to farther places, maybe to even get into places that we weren't able to with the Apollo missions, like be able to look into these permanently shadowed regions, or these areas that have never seen the light on the lunar surface. And as I said before, it's a moon and Mars exploration. The moon is sort of the first accessible place where we can try a lot of this technology, where we can do a lot of these exploration scenarios, where we can do sampling, where we can really set up a really good system for us to be able to expand how much we want to do from a science exploration perspective. But we're also looking towards into the future of getting to Mars and doing the same thing there. And Mars is a totally different environment. It's got a little bit of an atmosphere. It has a history of having water, of having an atmosphere. There's potential for life on Mars, even to this day, if it's been kept deep enough, I guess. And it's really the next step and a really interesting place to go that we all really want to go to. But right now, the moon is sort of the next step, and it's going to hopefully give us a lot of information about not just exploration and what we can do on another planet or another on the moon, but also it can give us a lot of insight and a lot of information into how our solar system formed. It can show us a lot about what the early Earth was like. The moon has captured a lot of the history from Earth itself, that over millions and billions of years, the Earth has undergone a lot of changes, but the moon really hasn't. It's been impacted quite a bit, but the surfaces have been there for billions of years. So they can show us a lot about what the early Earth looked like and was made out of. And with that, I'm going to go ahead and end, and I will take any questions. I'll go ahead and stop sharing.
Thank you, Ross. Let's see, I'm trying to find my own video in here. Everybody thanks Ross for his presentation. We're going to do about a half an hour of questions right now, and we will take questions a multitude of ways. You can ask questions either by raising your hand, and we can call on you and you can unmute and show your video and ask a question. Or if you don't feel comfortable doing that, we're happy to also take questions in the chat. In that case, I'll probably read it out so that Ross can focus on answering it. All right, so, and we're just going to apologize in advance. I'm reading names off of your Zoom name, so if that's not your real name, I'm sorry. And also, if I mispronounce it, I also apologize. So I'm going to pin myself here for a second. All right, I see one raised hand from Bo. So why don't you go ahead and unmute yourself and ask your question? Go ahead.
So what would be the process of making fuel out of the frozen ice?
Yeah, that's a great question, and it's not something that I do on a day-to-day basis. So there's probably better answers out there. But the idea is that what you're worried about with the what we call volatiles or the frozen ice, frozen water, whatever you have down there, is to try to get oxygen out of it. Oxygen is really the important thing that we need to get out to be able to basically make fuel on the surface of the moon. So if we can get oxygen out of there, we can start producing propellant or fuel based on oxygen. And that can allow us to not bring so much water or oxygen from the Earth to the moon. And the biggest thing whenever you're doing space flight or launching anything is mass, or how much things weigh. The more things weigh, the harder it is to get up into the air and to space. So wherever we can save on the weight of the rocket that's being lifted off the ground, the better.
All right.
Okay, that's all I wanted.
Thanks, Bo. Okay, I'll ask a question from the chat here, from Leisha in Idaho. Do you think there could be living things in the moon caves?
Well, I'm hoping. Who knows? But it's probably not. The moon is not the most habitable place in the solar system. Mars has a lot more going for it. Like I said, Mars has an atmosphere, so it's very thin. But in the past, about 3.5 billion years ago or so, Mars actually had. My light went up. Mars actually had water on the surface. It had, air that, you could, but not us, but someone could potentially breathe in. So you had all sort of the ingredients for life on Mars, but on the moon, we just never really had that. We never had water on the
I'm
surface.
halfway listening. My kids have to attend two NASA Zoom expert
Somebody,
meetings.
So the moon never really had much of a chance to have a lot of life, and one of the things that we try to do whenever we do space exploration is what we call planetary protection. So whenever we visit, either with humans or with robots, other planetary bodies like the moon or Mars, we try to make sure we don't bring anything from the Earth, any kind of bacteria or microbes, anything living with us on our spaceships to that place that we're going. The problem is when Apollo was doing this, the planetary protection wasn't quite as rigorous as it is now. So if we find things, that they won't be living things in the way you're probably thinking of them, like I don't know, like lizards or anything like that. It'll probably be microbes or bacteria or something like that that can survive the radiation environment and the really cold and no water, no atmosphere kind of environment.
Okay, great. All right, we'll go next to Esmeralda. She's had her hand up. Do you want to unmute yourself and ask your question?
Hey, Esmeralda's not me. That's my teacher.
All right.
I kind of wanted to ask, what are your thoughts on when we'll be able to colonize Mars with people? Like in what time frame?
Yeah, colonizing Mars. That's a commonly asked question. It is it's it's difficult. We have to get there first. We have to really get there and see if we can even survive there. And even getting there and surviving is really difficult because in space, you don't have any protection against radiation from the sun, from your near environment. There's a reason why we send robots to all these places first, is because it's really hard to get people there. We're a lot squishier than robots. So, if a robot gets exposed to vacuum, not a whole lot is going to happen. But if a human does, well, that's the end of your mission there. So we're, getting to Mars first is going to be a huge leap for us. And colonizing is going to be way, way, way down the road from there. Because, like I said, Mars, it hasn't seen an atmosphere, a real, a thick atmosphere. It hasn't seen flowing water. It's been exposed almost to vacuum for, almost 3.5 or more billion years. So it's changed quite a lot. But at one point, maybe it did look a lot like early Earth. So you never really know. But in terms of getting everything we need to Mars to be able to colonize it, that's a really, really big program that you have to run. So
yeah, your statement on how we could use the moon to go to Mars, that just kind of interested me.
Yeah. I mean, if we can use the resources that we have on the moon to make fuel to go to Mars, it's a lot easier to actually lift a rocket off of Mars or off of the moon than it is from Earth, because you don't have to deal with as much gravity. You don't have to deal with the atmosphere. And you have resources right there that you can make propellant out of.
All right, thanks. That's good from an expert.
Thank you. All right, I'm going to ask another question from the chat here. This one is from Paige Graff, who you may know, but I think she wants you to describe. Do you ever participate in tests outside of your lab to help prepare for the Artemis mission?
Yeah, we do at Johnson Space Center. We do quite a bit of testing with other NASA centers as well, with a lot of universities and even industry partners, where we go out into places all over the world, Iceland, Arizona, and we do test of equipment, of hardware. How does it work out in the field? Or even just how do we sample materials? Like if you have an astronaut and they're walking around on the surface, what do you tell them? Sorry, my light keeps going off. What do you tell them? What sample to choose from billions of rocks on the surface? Which sample to go for as an astronaut? And training them to have that science background is a big thing that we do here at JSC. And we do a lot of tests even outside here at JSC. We have a rock yard that kind of looks like the lunar surface that we can do some testing in. And we're always developing new ways of testing outdoors. So yeah, not just in the lab, also outdoors and also all over the world.
Awesome. That's always a fun thing to think about if you like being outside and like doing outdoorsy stuff. You can have it all.
Yes.
Okay, we're going to go do another video. The students at Keller Elementary in Mesa, Arizona, if you guys want to unmute and ask your question, go for it.
She's moving closer. She'll be right there.
Okay.
Was it confirmed that we do have water on the moon?
Yeah, that's a good question. So we have had missions that are orbiters that have actually one in particular called L-Cross that you can look up. And what this orbiter did, or this little spaceship, I guess, just a little orbiter, it has actually crashed into the moon on purpose into a crater, so it could actually, as it crashed and it sent up a bunch of materials outside of the, up as from impact, it actually quickly checked what was in that material. And what it was able to find was that, hey, there's some water in here. And that was a really big surprise to a lot of people. There's some water vapor in here. And that could be from these water ice, or ice deposits that are buried below the surface. Now, so we do have data saying that, and even in some of the minerals that are on the lunar surface, you can find water that's sort of in the minerals themselves, but it's not like liquid water that you would have on the Earth's surface. And the other thing with we always say this word volatiles. Volatiles is a sort of, everyone gets worried when we say volatiles, but the reason why we say volatiles and not just ice or water ice is because there are other things under the subsurface that are not as nice as water ice that we don't really want to come in contact with, like methane and other things that are something that you don't really want to be around. So yes, there, as far as we can tell, there is some subsurface water ice, but there's also other things down there, and we don't really know how deep it is. We don't really know how much of it there is, but there's plenty of people that are trying to figure that out. Good
Great.
question.
Good question. Yeah, we've got lots of questions in the chat, so I'm going to throw another one out, and you may not be able to answer this. I know that it's hard to say, but if there is an Artemis 4, what would that mission be?
Yeah, an Artemis 4 mission would probably look a lot like an Artemis 3 mission, where we have boots on the ground and doing exploration. It would be very modeled very much on what Apollo did, and just with every mission you kind of go out a little bit further, do a little bit more science, maybe get some more science instruments on the lunar surface, and expand basically your footprint from your landing site, which is basically what the Apollo did with Apollo 11 and with every mission after that. So the Apollo 4 or Artemis 4 would look very similar. I mean, we would just be sizing everything up and going a little bit bigger. But a lot of these things also sort of change with time. We're looking at years down the road, so things can always change a little bit. But that's currently what we're thinking.
Okay, I'm going to ask one more from the chat, and then I will go next to Red Lodge. But first, from Thompson Falls, Montana, this is a good one. What does someone with your job do day to day? What does the work entail, and how long have you been doing this for?
Yeah, great question. I'll start with the last part. So I've been doing this for just actually this month is going to be 3 years. So I've been doing this job for 3 years. And my day-to-day varies every single day. It is something totally different. So, I mentioned in the presentation that I work with these lunar simulants. That's one of the hats that I wear here, where we basically help with testing of hardware in this planetary analog materials, these lunar simulants, to make sure that we're ready when we go to the moon's surface. But I also do several other things that are sometimes a little bit more hands-on, sometimes a little bit less hands-on. I help with doing what we call science integration. So making sure that science gets a seat at the table whenever we look at things like a lunar terrain vehicle or a pressurized rover, or even how we would use the geology tools on the lunar surface. And a lot of that is, sitting in meetings and reviewing documents, but it can also be really cool to be able to go and test these things in different places in the world, and to be able to basically come up with scenarios where you can actually use the instruments that are going to be flying to the moon in the way they're supposed to be used.
Sounds really cool. Yeah. Okay, we're gonna go next to a video question. So the folks in Red Lodge, Montana, do you want to unmute yourself and ask your question?
How many science experiments have you done yet?
So science experiments. Well, I've done quite a few. I don't know if I can count off the top of my head, but plenty. And you know what I would say is that some of them, you probably wouldn't want to present at a science fair. They're little experiments, but I feel like they all really count, even on a day-to-day basis. If you want to do a little science experiment, I would count that, because that's how you kind of get interested. That's how you keep going. It's just being curious. Keep being curious, and everything else will sort of come as long as you keep going. And by the way, Red Lodge, Montana is an awesome place. I've been there several times, and you guys have a really cool mine up there called Stillwater. And that is where we actually source, or where we actually take some of the materials that we use in simulants, is from the Stillwater mine in Montana.
That's awesome. How cool is that, guys? All right.
Yay!
Yay. You're closer to the moon than you think.
Yeah. Oh, yeah.
Okay, let's see. I'll ask another question on the chat here. Let's see. I'm just kind of picking through here. I kind of liked one at the end. Are there any elements in the regolith that scientists think could be transformed into useful compounds for creating structures on the moon? So you talked about rocket fuel, but what about, have you looked into creating structures on the moon?
Yeah. Oh, yeah. That's a big question right now, is if we can use the material, not just for propellant or for food source or whatever, but for building habitations, building structures on the moon. And there's a lot of groups that are looking in this all over NASA and all over industry. People thinking about doing things like 3D printing big structures with the lunar regolith, and actually building, things that you can live in potentially on that kind of scale. But in general, what we call in situ resource utilization, which is just a fancy way of saying using the dirt that is under your feet to build stuff with. People do a lot of that. They care about a lot of the elements that are in the regolith. I talked about oxygen earlier, and not just for propellant, but for a lot of other things that you need oxygen for. They also care about metals, getting metals out of the ground, like iron. There's iron down there. There's helium down there, helium-3, which is a very major resource that we don't really have on the Earth. We can't really mine helium-3 very efficiently, or in large enough amounts on the Earth. But on the moon, it's there. And it's a big thing that people are looking into, of how to use, or how to mine it, how to use it, how to process it, melt it, do all sorts of things. So there's a ton of stuff in the regolith itself, just the rocks and the minerals, that people want to use for building things on the lunar surface.
Awesome. I love the idea of being creative on a new planet. Like we did that on our planet and figured out how to create things out of the soil. So let's go do it.
It's a little bit harder, but not impossible.
Yeah, a little harder when you can't breathe the air, but hey.
Yeah.
Okay, Callie, you've had your virtual hand raised for a while. Why don't you go ahead and ask your question?
When we do get to Mars, will we bring the broken rovers back to Earth and repair them, or use some of the parts that work for a different robot, or like a rover? And is there some way of sending the rovers to Mars that makes it more cheap, but also more efficient?
Yeah, that's a great question. That's always a really hard one. With you want it to be efficient, not use as much fuel or not be as heavy, but you also want to make sure you're able to do the things that you want to do. The nice thing with sending robots, again, is you don't have to worry about people's lives. So you don't have to worry about things like radiation shielding or shielding from the radiation of the sun as much as you would with people, or even things like, I don't know, feeding them, providing them air, providing them water, or things to basically live off of. So there's definitely an upshot of having robots do some of the exploration for us before humans do. Now, to answer your question, if we're going to be reusing the rovers that are currently on on Mars, no, as far as I'm aware, there are no plans, and we kind of want to expand our like where we go. So we don't necessarily want to go to the same exact locations where we've been before, but we want to kind of go to different locations. The only exception is with the Perseverance mission, which is the current mission that's on the lunar or on Mars that's active right now. There are 2 rovers currently active, one of which is Perseverance that was launched in 2020. It's actually leaving little samples for us all over the place for a mission that will be coming later to actually pick those samples up and bring them back to Earth, our Mars sample return mission. So hopefully at least one of those rovers will see someone else, landing next to it and picking up the samples, but not really messing with the rover Perseverance itself. Great question.
This is a great question. Okay, I'm gonna spin. We've got a lot of questions, so I really apologize, guys, if we can't get through all of them. But these students are thinking, and you may not be able to answer this because it's probably the wrong space center, but they're thinking a little bit about growing food on the moon. So you mentioned, right, it's nice that you don't have to feed the rovers food. So do you know what the biggest challenges are for growing food on the moon and how difficult it is to grow the plants in the regolith? Do you know much about that?
Yeah, my lab deals a little bit with providing materials to groups all over the country and even internationally that try to grow plants in regolith. The big problem is the nutrients that we just don't have in regolith. We don't have microbes in lunar regolith, right? Little critters to be able to provide nutrients and break things down in the regolith. And we also obviously don't have liquid water in the regoliths. That's something we have to add and provide nutrients as well. And there are other ways of growing things that don't involve regolith directly, like hydroponics, but that's using a lot of water, which is not what we have a lot of. I don't really want to bring a lot of with us when we go to the moon because it's expensive to bring liquid water. But also there are, there have been studies done in the past and that are currently being done with finding out ways of not just how we can grow plants in the lunar regolith itself, but maybe there are some plants that work better that are a little hardier, that can withstand some of the things that not just in the regolith, but also the lunar environment. Like I keep talking about radiation, right? There's no atmosphere, so you just get a bunch of radiation coming directly from the sun that nothing is stopping it. So you have to protect the plants as well. But there's a whole lot of folks thinking about that question, and it's a big one. And we're trying to help them figure it out. But that's something that I'm not directly involved in, but definitely know that a lot of folks are working on.
Great. Yeah, and there is another, it's not really a challenge, it's another science project for K through 12 students called Grow the Moon. So if you guys are interested in that, that's also another opportunity to actually collect some data for NASA to help understand what kind of plants would be hardy and successful on the moon. Okay, Ross, I'm gonna have you do 2 more questions.
Yeah, no worries.
And then if you're okay, and then we'll close her down because we're right at 5 o'clock our time. Here in the Pacific Northwest. So there was a few questions. This can be short, but curious about colonizing planets other than Mars or going to the moon. Are there other places in the solar system where NASA might want to send people to live?
Yeah, I mean, there are other places that are of interest. I won't say colonizing because that is a very difficult thing from a technology perspective that's really, really, really hard to do. But there are other places in the solar system that scientists are really curious about going to and getting information from, because their surfaces may be harboring life in the subsurface, or at least are capable of doing it. Places like some of the moons of Saturn, like Titan and Enceladus, those are Europa. Those are really big points of interest to scientists that really want to study habitability of, being able to survive life, being able to be on another planetary body. So those are good ones. It'd be much harder to go to some of the other planets because they're either too far away from the sun, or too close to the sun. And they're either too big or too small. They have no atmospheres, or they're just made primarily out of gas and have really thick atmospheres, and we can't really get to them anyway. So right now, prime candidates are more, lunar surface for doing exploration work, and then Mars is sort of the prime candidate for everything else.
Awesome. Okay, so one final question. This one's kind of a mix again of a few, and a nice way to close it off. So, I mean, I think you've demonstrated today that working for NASA is really cool. You get to learn, you get to do hands-on stuff, you get to travel the world, you get to learn and think about some really interesting topics about what we humans might do in the future. So we got a lot of middle school students here. We've got some high school students. So maybe I'll just ask you to put yourself in their shoes, try to reflect on what it was like to be their age. And maybe if you could say a little bit of something from your life experience about maybe overcoming challenges, or some advice that would help these students achieve their goal if their goal was to work for NASA one day like you.
Yeah, I think that's a great way to end and reflect. Yeah, I would say, to my point earlier, being curious, really wanting to investigate, and really having that sense of a wonder, like how do things work, why do they look the way they look, where can I go to find out more about them. That curiosity was really, at least for me, something that really drove me to wanting to look at space exploration as a career choice. And when I was earlier on in elementary school or middle school, I had no idea what I wanted to do with my life, right? It's hard. And when the best advice I can give you is enjoy what you're doing, and have fun with it. Follow what you really love to do, and don't put so much stress or strain. If I was in elementary school or middle school, I would never have been on a Zoom call with a NASA expert. So you guys are way ahead of me already, all of you that are on this call, in terms of getting to this end. So, being curious, believing in yourself, just trusting that you're able to do things, having confidence in what you're doing, I think is really important, and not giving up, just continuously working. Like at the very beginning of this call, like I didn't start looking at space exploration and as a job. I was a lot more interested in history and then even business. But there are certain things that you just have a passion for, and even if it takes a little bit longer to get there, you trust that you will get there, and you do everything you can to do that, and keep that curiosity going. It's always good to have in the back of your mind. It really helps a lot, even now.
Awesome. That's some great advice, guys. So stay curious. Stay curious. Okay, well, we'll wrap it up there. Thanks everybody for joining us this evening, this afternoon. Everybody say thank you to our speaker for spending some time with us today. We really appreciate it, and I learned so much, and I really appreciate all the time you spent answering our questions. So feel free to sign off, guys. Everybody say thank you, and we'll see you for the next NASA Expert Talk.
Thank you all.
Thank you.
Take care.